Okay, great. Good. So to provide you with all the information required for doing your first assignment, and also with the short introduction into the field of statistical simulation and computer-intensive methods, I wanted to start out with a few of the buzzwords which are related to these fields. There's artificial intelligence related to this, machine learning, big data, data science. Some of you are actually doing the master studies of data science. So these are the big words, and they always include more than just statistical simulation, but all of them do include statistical simulation. So let's talk a little bit about differences between human beings and computers. Do you have on some way the slides available? So human beings would round both of these numbers if asked to do so, always to the next smaller number. Oh, that was not it. Sorry, I just have to help the ones who are actually sitting here to also be part of this. Okay. So both numbers look more or less the same for human beings. You have to look very closely to see that one has an additional 9 at the end. For a computer, it makes a big difference. It's not like both of them are always rounded to the next smaller number, but the second one is already being pre-rounded. And as soon as this gets 1.5, because there's one number too much, it will be rounded up to 2 instead of down to 1, which is absolutely not reasonable for a human being, but absolutely reasonable for a computer. So we will first start out looking into what can go wrong if you do not use this simulation with foresight. And we will therefore look at the implementation of different types of formula in different software systems, libraries, and packages. And you will also look at the usage of memory and computation time for this. And the example for doing this will be variance calculation. Variance calculation, we are more or less aware that the variance itself is measuring the quadratic deviance of numbers from their expected value. And therefore, typically, there are two types of variance formula, the one which is for the whole population and the one which is just for a sample, with x bar being the sample mean. Now, there's also trivial decomposition of the variance for the mathematician, something that all the others have tried to forget in the past, since their last math lecture. For the non-mathematicians, the variance decomposition formula splits up the whole quadratic deviance term into having a part which is the expectation of the squared values minus the original expectation squared. So this also provides us with a second type of formula. This is the sample version of the second type of formula. We have the sum of all the squared values plus the mean squared. And of this, we take the adjusted mean. For those not so well aware of the reason for this dividing by n minus 1 instead of n, if we do have the full population, we will not have a problem, as we are anyways observing every single part of the whole population. But when we only use a sample, we want to guarantee that the asymptotics of these estimators are correct. And asymptotically, we have to divide by n minus 1 instead of n in order to reach the right value for the variance. So as we will look at samples only, we will use always the asymptotically corrected version with dividing by n minus 1. And the next is, okay, we want unbiased estimates. And we will look at 4 algorithms in R to provide us with unbiased estimates for the variance. The idea is it's always the variance. Mathematically, it's all the same. It doesn't matter if I split it up or not, it is mathematically identically. However, for us, rounding those two numbers should also lead mathematically to the same result. It should also always lead to 1. However, it does not. So we're not looking into a mathematical problem, we are looking into a computational problem. If we use different formulas for estimating the very same thing, the variance of a sample, we will get different results, which is not good. Therefore, we will compare different algorithms, or you will do so. I already did that. You will use first algorithm 1. This is the basic variance calculation method used in R. We compute the sample mean, and we do compute the variance as we did above. Subtract all the values from the mean, square this thing, sum it up, and divide by n minus 1. Sounds good enough. Then there's second version of the algorithm. This is what Excel did previously in the old days of the beginning 2000s. Excel used this decomposition formula. Because it's super simple to sum up values, Excel just did this summing up. It used the squared values and then the squared version of the original mean, summed up the squared values, and then calculated this second formula. And this will be algorithm 2 for our comparison. And then let's talk about the concept of scale invariance. There's the property of scale invariance, which means it doesn't matter if I use a different center reference point for calculating the deviation from a certain center. So it should not matter if we measure our temperature in degrees Celsius or degrees Fahrenheit or in Kelvin. it has, in particular, Kelvin and degrees Celsius, they use the very same scaling, but they use different 0 points. And therefore, this scale invariance property talks about using different reference zeros for calculating things. Deviation should not depend on which value I use for a 0. Otherwise, I cannot trust anything I'm calculating anymore. And this is a basic property of variance calculation. Therefore, we will use as a third algorithm for this comparison the shifted variance calculation. We will use, instead of the original points, the points shifted by some constant c. Again, the point shifted by some constant c. This is the variance decomposition formula, but with a shift of a constant. One question which you will be asked to work on through your assignments is, what is a reasonable value for this c? And in order to initialize this, use the first value of your sample, and then find an argumentation what would be reasonable to use here as this shift parameter. The fourth algorithm will be the batch algorithm for doing this online. Thank you. So in order to do online calculations of variances, in order to do this in real time for doing time series measurements at weather station or being in finance, trading, economics, all these get real-time data. So with every new second or every new minute, every new measurement, the variance changes again and the mean changes again. And therefore, we use a batch version, an online version of calculating the means based on the previous mean and the new value which I observed now. And in addition, this variance correction formula for adapting the estimated variance. So this gives us a fourth option of possible calculations for such a variance. If you do this, you do it more or less going through your sample step by step, and every next value of your sample is observed like the next observation. In the online version, you do not really do it online. So we start out with the first two values for calculating the mean and the variance. And from then on, with the third to the nth one, we do the updating and compare also the variance which comes out of this fourth algorithm. Sounds more or less reasonable? All these are variance calculation algorithms. All these calculate the variance of the very same sample, and mathematically, they should all be identical. However, computationally, they are not. And this is the comparison you will look into. You will first look into simple vector with mean 1 and mean 0 and where deviance 1, and then one which is shifted to having its mean at 1 million. In all your exercises, I just wrote set seed 1. you will all write your own immatriculation number as the seed of your exercises, because this is the personalization for your exercise. Okay, just to make it clear. So all of you should get different numbers and different pictures because of that, because each of you has a different immatriculation number. So in R, there are several functions for comparing values. The logical comparison, the identical function, the all equal function. Use all of them and try out which is reasonable and which is not for what we are doing here. So you will get 4 different results for the mean of, for the variance of this, and you will get 4 different results for the variance of this. Okay, so take a look at those variance calculations, compare them against each other, and in the second step, when you run these different variance calculation algorithm, use micro benchmarking in order to get run times. This will run the thing for 100 times or however many times you want to do it. Do this with all the different variance calculation functions. Visualize that thing as box plots and compare it, and this is why it says 5 different functions, compare it to the standard implementation of R, of the variance. So this is our gold standard for comparison, R's variance calculation, the internal one, and then you will implement the 4 algorithms which I provided you on the slides before. So you do have 5 results and 5 functions for benchmarking here. So in the end, this should look something like this for your 4 algorithms. This will be the output of the benchmark, micro benchmark packaging. You will get one which is the precise one, which is comparable to the original R function, the one which is from Excel, the shifted one, and the online version. What we see immediately is that this thing looks really efficient for the Excel algorithm. So they were not stupid implementing it. However, if you look at the actual estimated value for the Excel algorithm, when you have 1 million, this shift with a center of 1 million, it looks terrible. Okay, so this implementation, this split up form really fails with big numbers and big means of our values. However, it's super efficient for calculation, but getting somewhere wrong much faster is not helping at all. The other ones look more or less the same. You see immediately that you pay a price for being flexible and doing online calculations. Yes, you can adapt it to every new value which is coming, but you pay the price in computation time. So what we would like you to do is do this and also add a 5th line for the original var implementation of R, and comment this regarding the performance and regarding the quality of the outcomes. Okay. Also, the computation times, here the log computation times for the different algorithms with the different means. Excel beats them all regarding computation time, but not regarding quality of our outcomes. Okay, so what you should take home, what is sometimes forgotten in machine learning, is that speed is not everything. and you would do well in implementing two different versions of getting you somewhere, comparing not only the computation times, but also the quality of our results and trying to get some kind of gold standard to compare against. This is validation of algorithms, typically in that kind of field. So even though one algorithm is always the fastest one, it's the one which is least robust against big numbers and big changes. Then there's the concept of condition number. I'm not absolutely sure if every single one of you has ever heard of this. Condition number is mathematically defined as something similar to the derivative, to the difference quotient in changing a little bit of the income and changing a little bit of the implementation. So for the variance, the condition number is defined in such a way. It's mainly based on this quadratic form of the absolute of our actual values, and therefore the conditioning depends on the mean value divided by the sample variance. As long as this is greater or equal than 1. How can it happen that this is not the case if we have super small numbers? Then it breaks down. Okay, so in order to try this out, that this conditioning holds, also look at the case which we did not use here for the comparison. We only used a very large mean case. Now you use a very, very small mean case, meaning something like 1 over a million. Because with 1 millionth and a very, very small variance in addition, not just 1 as the variance, but something very small and very close to that, you will see that this is not holding anymore. For the shifted variance, so we were asking you before, and you should try this out with the shifted variance algorithm. Start it with the first value of the sample. Try it out with different values. See what happens. According to the condition number, this algorithm performs best if the value by which you shift is the mean. Try to show this with simulations that this actually holds true. The best I can get in conditioning will be the result when the shifting is the shifting by the mean. And try to find a mathematical argument. If you're from the statistics mathematics direction, try to find the according mathematical algorithm or argument why this has to be true. Okay, this leads us to the end. So implementing these procedures will require you to have a certain understanding of the methods which you're implementing, okay? Like splitting up the variance into subsums, being able to shift, being able to update online. So we do require at least an idea of what a variance is and what a mean is, and we will gradually build up and start with random number generation and then build up modeling where we do bootstrapping, then go also revise a little bit of the basic statistics and look at it in a different light, in the light of computation. Because not everything which is mathematically cool and convenient is something which is good for computers. It might be that what is mathematically a very nice form for doing calculation completely makes your computation break down. But we will never know before we tried it. So that's why a lot of your things here will be trial and error, simulating things, see what comes out, and learning from failure what to avoid and how to check what can go wrong. Okay? So very simple. All that we did today, these 4 functions which you will implement yourself, plus the R's original variance function, comparing those regarding their outcome, comparing those regarding the function performance, and looking into conditioning numbers, finding a reasonable argument for variance shifting. This will be what you will do for your very first exercise. So it should not be beyond anyone's scope or capability to do this. But please take your time to do this properly, to comment all the things properly, to get a good way of documenting your results and your insights. Okay? Always, when you have numbers, provide tables and provide some kind of visualization, because this is more readable for humans than a lot of tables and a lot of numbers. Good. This should be more or less clear. Any questions regarding that? If not, thank you for your attendance online or in person. And I will stop the recording and provide you with the recording online.